Alright, so today we're going to do this change of variables problem, which essentially allows us to switch what we're integrating with respect to. So first we can notice that we can basically approximate f of si delta ai. So when we take n smaller and smaller and smaller and smaller, for any si on the interval xi minus 1 xi, this will basically be approximately equal to this, or converge to that. And we know that because we know that if f is a Riemann integrable, then and also the upper sum minus the lower sum, there's this partition such that it's less than epsilon, we know that ni equals 1 f of ti delta ai minus ab f dA is less than epsilon. And this is a theorem from Rudin. And ti is just an arbitrary point between so ti is just in xi minus 1 xi. Okay, so this is approximately equal to this, and then this is approximately equal to I equals 1, same thing. We can just take like the same point, just to make things simpler. Delta xi. All right, so let's show that if one is Riemann integral, then the other must be too, by just showing that they are arbitrarily close to each other. Thus, if one converges to value, then the other must also converge to the same value. So let's do that. Take the absolute value of n of si alpha I minus, oh, silly me. Well, first we have to make it so these kind of look more similar to each other. And how we're going to do that is using the mean value theorem. So, by the mean value theorem, alpha of xi minus, there exists a k in xi minus 1 xi such that minus 1 over xi minus 1 is equal to a prime of k. And notice that this just gives us that delta alpha I is equal to a prime k times delta xi for some k in xi minus 1 xi. That makes things a lot easier. So this means this is essentially just going to be equal to prime of k. All right, so now we can subtract these, and we can see that when we do that, we can factor out this delta xi, and also notice that because f is bounded on this interval, there exists m in R such that f of x is less than or equal to m for all x in a, b. So this will be less than or equal to m. This will be less than or equal to m. And we will hence be able to factor out the m. And just make m positive, just to make things easier. All right, so then we can simplify this to be less than or equal to m times delta of the sum from I equals 1 to n of a prime of k minus a prime of si times delta xi. And notice that because a prime is Riemann integrable, we know that by the integrability criterion, there exists a partition P such that u of P f alpha prime minus L P f alpha prime is less than epsilon. And because this is true, we know that basically this will be less than, we can make this epsilon over m, and we can make this whole thing, right, less than or equal to less than epsilon over m. And that's just going to be simply because we can choose a partition such that this is true, and this will be bounded by the difference between the upper and lower sums, because obviously this will be less than or equal to mi minus mi, because this will be the maximum kind of difference between the outputs. Okay, great. So now we have this is less than epsilon. Thus these are arbitrarily close, and if f is Riemann integrable with respect to a, if and only if f(a) is Riemann integrable with respect to x. All right, so now let's show that these are equal. Okay, so in order to do this, we use our theorem here, which tells us then that actually, well, as n goes to infinity, this will be equal to this integral, and this will be equal to this integral. And since the difference between them is less than epsilon, they must be the same. So we have our final fact that these are equal. And we're done.